All right, getting ready to. We are starting our first couple problems here with adding, no subtracting, just adding some binomials. Now remember, binomial just means, like it sounds with the bi, it means two terms. What we're doing here to add them, though, we don't do anything differently because they're binomials. It's really a matter of just ignore the parentheses and add like terms. Okay? So for adding binomials, adding any kind of polynomials, just combine like terms. So 2x and 5x makes 7x. 7 and 3, positive 10. It is just that simple. That can't be simplified any further because this term has an x, the 10 doesn't. Number 2, 8x and 3x makes 11x. 3 and negative 4 makes minus 1. 6x, positive x makes 7x. Negative 1 and negative 10 is negative 11. 12x plus negative 4x is 8x. Negative 3 and positive 3 is 0. So there is no constant term. We have just 8x. And number 5 here, negative 5x plus 7x, 2x. 2 and negative 13, negative 11. Now, to multiply binomials, we do have certain shortcuts, or a shortcut, that we will be learning for multiplying binomials, and it will only work for binomials, no other type of multiplication of polynomials. This, though, says to use the distributive property, and that would work no matter how many terms are in the first or second set of parentheses. So, distributive property, remember before, was something like this: a times quantity b plus c is equal to ab plus ac. So you took what was in front of the parentheses and distributed it to all the terms inside. Well, we just need to extend that, like by one step, to say if there's two things in the first parentheses and two terms in the second parentheses, what we have to do is distribute everything in the first set to everything in the second. So it would be a times c, also a times d. Then we would turn around and do the same thing with the b. b times c and b times d. You may or may not have like terms after all that as another step, but that's what they mean by distribute. Everything in one parentheses gets multiplied by everything in the other parentheses. So in this first number 6 here, 2x times 5x would be 10x squared, because we're multiplying an x times an x. 2x times 3 would be 6x. Now doing the 7. 7 times 5x is 35x. And 7 times 3 is 21. Now we do have to take that next step and say, do we have any like terms? And yes, right here in the middle, 6x and 35x makes positive 41x. The other terms that you didn't add to or with anything else are just brought down as part of your simplified expression. Okay, so this is where you need to be when you're done. Number 7, 8x times 3x, 24x to the second, and 8x times 4, 32x. 3 times 3x, 9x. 3 times 4, 12. We do, again, in the middle here, have like terms, so we end up with 24x squared plus 41x plus 12. Number 8, 6x times x, 6x to the second, negative 60x. Negative 1 times x, negative 1x. Negative 1 times negative 10, positive 10. In the middle, We have a set of like terms, so we end up 6x squared minus 61x plus 10. Number 9, 12x gets distributed, makes negative 48x to the second plus 36x. 3 gets distributed, becomes negative 12x plus 9. Like terms again in the middle two terms, so negative 48x squared plus 24x and plus 9. It's also a good idea, not necessary exactly, not wrong if you forget this, but it's a good idea to get in the habit of writing these resulting expressions in standard form. And what we mean by that is going from highest exponent to none. So x squared, then x to the first, then no x's at all. All right, number 10, distributing the negative 5x. I see negative 35x to the second plus, since a negative times a negative is positive, 65x. Distribute the 2 times 7x, 14x, 2 times negative 13, negative 26. Like terms in the middle for negative 35x squared plus 79x minus 26. And the last one here in this set, x times x, x squared, x times negative 5, negative 5x. Distributing the positive 5, we get a 5x minus 25. Now something a little different, a little special happens here. These two middle terms, which are alike, negative 5x and 5x, those are like terms, they cancel each other. It becomes 0x. And we never write 0x, that's unnecessary. So these are canceled, and we just have x squared minus 25. Now, what caused that to happen was having the two binomials be lookalikes with the exception of one's a plus, one's a minus. Every time you have that situation, you are going to get an answer, a simplified expression like we saw here. And it even has a name. It's called the difference, since the answer has a subtraction sign in it, of two squares. 2 because it's only a binomial rather than a trinomial as we saw in the last 5, and 2 squares because each of these terms are a perfect square. X to the second is a perfect square, so is 25. All right, turning the page, we're looking at some rectangular shapes. Are they all squares? Yeah, no, they are some type of rectangle, including squares. So we need to refresh our memory. Area of any rectangle, that includes squares, is base times height, base times height, or length times width, if you learned it that way, same thing. Perimeter just means you add all the sides. Now there is a formula for perimeter of rectangles, and it is perimeter is equal to 2 times the length plus 2 times the width. So if that's familiar to you, feel free to use that. This description of perimeter here would work for any polygon, any number of sides. This one is just for rectangles. So the perimeter in number 12, well, since we know they are at least a rectangle, the opposite sides are all congruent. So all 4 of the sides here are x. So if I added all 4 of those together, I get 4x. For the area, now I need to multiply x times x, so that area is x squared. Number 13 is another square. I know that due to the two dimensions being the same. So another x plus 1 on the left and another one on the bottom. So for perimeter, if I'm really adding 4 of those together, the shortcut for doing that is to say I'm going to do 4 times x plus 1. Well, that's a distributive property issue. 4 times x is 4x. 4 times 1 is 4. For area, I would be multiplying x plus 1 times x plus 1. And that's what we just did in the 6 previous problems. We are going to use the distributive property to multiply that. X times x, x squared. X times 1 is x. 1 times x is x. 1 times 1 is 1. So when I simplify, I end up with x squared plus 2x plus 1. Now a rectangle. So not all sides are congruent, but opposite sides are. So the right side's a, the left side is a. The top is a plus 5, the bottom is also a plus 5. So for perimeter, adding all of those up, and I have 2 sides that are the length a plus 5, and 2 sides that have a length of a. So when I distribute and combine like terms, here we go, 2a plus 10 plus 2a, and 2a makes 4a plus 10. For area, I'm multiplying base times height, and it doesn't matter which one you call base and which one you call height, they're interchangeable. A times a plus 5. So once again, I have to distribute a times a and a times 5. That's a squared plus 5a. Number 15, another rectangle but not a square. So bottom is also b, left side is b plus 3. Perimeter, I've got 2 of the b plus 3s and 2 sides that are b. So distribute, that's 2b plus 6 plus 2b. Like terms is 4b plus 6. And the area, I'm multiplying base times height, b times b plus 3, I'll need to distribute. B times b, b squared, b times 3, 3b, not like terms. So my expression b squared plus 3b. Number 16. Now, both sides are binomials. They are different, though. So the left side would match the right. It's x minus 2. The bottom would match the top. It's x plus 3. So for perimeter, I've got 2 of each. 2 x plus 3s added to 2 x minus 2s. So 2x plus 6 plus 2x minus 4. Well, 2x and 2x makes 4x. 6 minus 4 is 2. For area, I'll be multiplying base and height. So x minus 2 times x plus 3. And again, like we did on the last page, we'll distribute with these binomials. So x times x and x times 3 gives me x squared plus 3x. Then distribute negative 2. Like terms in the middle, 3x minus 2x is 1x. So x squared plus x minus 6 is your area. And number 17, the right and left side have to match. The top and bottom have to match. And let's do our perimeter. Perimeter is 2 of each of those, so 2x plus 4s added to 2x plus 1s. As I distribute both, I get 2x plus 8 and 2x plus 2. Like terms gives me 4x plus 10. And then the area. Area would be base times height. So x plus 4 times x plus 1. And distributing this first x gives me x squared plus 1x. Distributing the 4 is 4x plus 4. Like terms here in the middle, so my expression is x squared plus 5x plus 4. All right, lastly, we're going to do some greatest common factor here, and you learned that a long time ago, elementary school. But greatest means the largest. Common means that they have in common, that they share. And factor is what was multiplied that went into the number. Now, these are different from elementary school in that they have variables attached. The variables will be the easy part anyway, so let's think about the numbers first. So 15 and 25. What you probably learned in elementary school was to do factor trees and identify what showed up in both. So we'll do it that way and then talk about how you could skip this for the future. 15 can be broken into 3 times 5. Both 3 and 5 are prime numbers, so that can't be broken apart anymore. 25 is 5 times 5, and again, the 5s are prime, so I'm done with the factor tree. And then you would go and identify, well, what numbers appeared in both? There was a 5 in both, and that's it. So you would have said your GCF was 5. Well, all we're going to do in addition to that now is throw some variables on here. So if this 15 also was multiplied by a, b, c squared, then this bottom row, my prime factorization, would also include an a b, a c, and a c. A, b, c squared means a times b times c times c. The 25 has a cubed b, c. So when I break that down to what it really means, that's a times a times a times b times c. So I'm going to go through and circle again the variables just like I did the numbers. So they each have an a, they each have a b, and they each have a c. Put that with the 5 that we had identified previously. So my GCF here for number 18 is 5 a, b, c. I'm hoping, keeping my fingers crossed, that you do not need to do a factor tree for all of these problems identifying GCF. So how can we skip that part? Well, we look at 12 and 32 and just try to ask ourselves, what is the biggest thing that goes into both? Well, the biggest thing that could possibly go into both would be 12. You can't have a larger one than the smaller of the two factors. So does 12 go into 32? And the answer is no. So what things do go into 12? Well, 6 does. That doesn't go into 32, though. 4 does. Yep, that goes into 32 also. And you might just try to check it the other way and go, okay, well, what else went into 32? And I know 8 does, but 8 doesn't go into 12. So for the number parts here, the GCF is 4. Now, for the variables, if you think, I shouldn't have erased it, but if you think about the little factor trees that we had before, what I circled was only one of each letter because there was no term that had more than one of each letter. So here, when I see x to the 5th and x to the 6th, what's the smallest amount I have? And it would be x to the 5th. So x to the 5th can definitely go into x to the 5th. It can also fit in x to the 6th because it's a smaller exponent. For the variables, I have y to the 1st and y to the 1st, so y to the 1st. Okay, 17 and 51. Well, 17 is a prime number, so nothing else goes into that. My only chance is, does 17 go into 51? Well, it actually does. So that'll be part of your GCF. Look, I have a P in both. I have a Q in both. I have an R and an R to the 3rd. Well, the most R's that could fit into each of these then is a single R to the 1st. Okay. Number 21, if I look at the numbers 7 and 21, 7 does go into both. X squared and x, the most I could pull out would be an x. Now I've got 3. Well, I do this the same way, except whatever I choose has to go into all 3 of the terms. So the smallest number here is 6. I can't go larger than that. So does 6 go into all the terms? And the answer is yes, it does. I've got an x squared, an x, and no variables. So I can't take anything but a 6. I can't say that a larger factor has an x because there is no x in this term. 4 and 9. Now there is no number larger than 1 that goes into 4 and 9, so my GCF for those is 1. And then x squared and x would just be x. Back to 3 terms here. So I'm looking at the numbers 11, 33, and 3. Well, the smallest of those is 3. So does 3 go into 11 and 33? No, it does not. It goes into 33, but not 11. So the GCF, the GCF of the coefficients is 1. Now the variables, I've got x squared, and x to the first. Well, the most I could use then would be x to the first. Got y squared, got y squared. They all have at least 1. Number 25, looking at the coefficients, 16, 24, 16. Well, 16 doesn't go into 24. The next largest factor of 16 would be 8. 8 does go into 24, so that's our GCF. A squared, A, and no A's at all, so I can't include any A's in my GCF. B squared, B, and B, I do have at least a B in all of those. 49 and 36 share no factors other than 1. S squared and S squared means I can use S squared. T squared and T squared, I can use T squared.